In this video, we're going to discuss the line spectra of elements, what that is, where we get it from, how it relates to photons, and what it helped us realize about the nature of light and matter. A line spectra is what you get when you take an element, put it in a vacuum tube, crank a ton of electricity through it so it just brilliantly lights up. If you've ever seen a fluorescent light, that's basically what you do. There's a little mercury vapor in there, and you light it up, and it starts emitting light. It takes a lot of current to do it. You have to have a really high voltage, but it's something we can do. Once we developed electricity, this was fairly easy. This is how neon lights and everything else works. This is also why you get those beautiful colors. You ever wonder why old-time signs from like 50 to 100 years ago, neon was so big? It's because they had never had those colors before. They just didn't exist. It's not that it wasn't possible for humans to produce them and contain them. Discovering we could do this led to a lot of, trendy signs. What's going on is that if you take that light and you put it in front of a diffraction grating or a prism or anything that will spread the light out, what we find is that while normal light, just from the sun, looks vaguely like this, it just kind of has all the colors. If you have one of the individual elements in a tube and you crank power through it, you don't get that spread. Instead, you get very specific little bits of light. And so if you have a sodium vapor lamp, if you've ever seen those kind of yellow lights that are on late at night on highways and the like, they're not very white, they're more yellowy. That would say sodium bulb. They last a long time, but they give off a mostly yellow light. And that's because instead of emitting the full range of color like the sun, that sodium vapor only gives off very particular wavelengths. And you'll notice a lot of them are over here in the yellow range. And so that light tends to be fairly yellow. If you do this with hydrogen, it gives you a different set of lines. And a different number of them. Each element, as you can see below, gives wildly different sets of lines. This was very puzzling. What was going on? If you're just heating something, you tend to get the full spectrum. In fact, if you just heat an object, instead of run electricity through it, if you just heat up a chunk of iron, what'll happen is, the iron originally isn't emitting any light, but it starts getting hotter. And what you'll notice is you start seeing these wavelengths emitted. And the hotter you get it, the more wavelengths start emitting. And by the time it's white hot, it's emitting all of them. If you just heat an object, you get what we call black body radiation. This is just something that used to be dark, now is so hot it is giving off all the colors of light. But if you run the current through them, you get these line spectra. Other things we noticed at this point in history was that, let's say you had a plate of metal, and you kind of had it rigged up to, I'll say a light bulb, but some sensory meter. And this was just a chunk of metal. Well, nothing's going on. But if you were to shine light from another source on it, and this light was red, and it hit the metal, and nothing would happen. You could have a dozen bulbs, you could increase the brightness over and over and over and over and over, and nothing would happen. But the moment you change the bulb out, got a new bulb, and this one was, say, blue, you would cause a current to flow. And suddenly, whatever your meter here would detect it. And it didn't matter if it was a dim blue bulb or a bright one. It didn't matter how bright the red one was. The red bulb would not cause the current to flow, but the blue bulb would. This was the photoelectric effect. Classical physics said that, hey, if you do something more, it should have a bigger effect. Put a 10-pound weight on a object, it pushes down with 10 pounds. Put 20 pounds on it, it should push down with 20 pounds. It should have more force. The idea is brighter red bulbs should just accumulate, but they didn't. Didn't matter how many red bulbs you used, it would not cause this electrical current to flow, but the weakest blue bulb would. This is where we discovered that the light was different. Blue light just did things that red light could not. This is where we started to see that color was representative of energy. This also told us something special in that the metal, what was happening, we think it was losing electrons. That's how the current flowed. Light hit, electrons left the metal, and so a current could flow. They could move to replace those lost electrons. Well, the red light just wasn't strong enough to do it. The blue light was. And so there was something about the electron where you couldn't push it out with a bunch of red lights. It had to be all at once with a blue light. And this is where we started to realize quantum mechanics. Now that might be a big word that science fiction movies and Marvel likes to throw in everything to explain anything, but all it actually means is set amount. That is it. Quantum mechanics just means a set amount. There is a set amount of energy in blue light. There's a set amount of energy in red light. There's a set amount of energy it takes to move an electron off the metal. That is all the quantum meant. Because the idea was if you could just pour lots of red in, it would be continuous. You could add it over time, like filling up a bucket with water. You can add a little bit and then add a little bit more and add a little bit more, and eventually the bucket will be full. But quantum mechanics says, no, you can only add them in certain size units. It is impossible to add it continuously. So there's a few different effects that we were seeing. How did this eventually come together and explain what was going on? What were the molecules doing that was so different from what we think of normal physics? The first step along this way, the one that really kicks off things, is the Rydberg equation. Rydberg just did a lot of math to that hydrogen line spectra. And what he found was he discovered a formula that said the 1 over the lambda was equal to some constant, which we call the Rydberg constant, and this weird relation mathematically. What he said was the difference of the inverse of the squares of two whole numbers times this constant happened to equal 1 over the wavelength. Now that seems odd at first, it seems rather complex, but if you do a bunch of math for the distances between the hydrogen line spectra, well, there's a difference between them in the difference of inverses of squares. The Rydberg constant gives us kind of our initial value here to multiply them by, but you'll see it's an escalating size increase between all those points. That is what this formula was able to calculate. People had spent their whole careers trying to figure out line spectra. To suddenly have what is a reasonably simple formula explain one of them was puzzling to say the least. The theory that eventually came was that there were levels. N1, N2, N3, N4, and so on. And that our electron was hanging out in one of them, and light could come in. And when light hit that electron, it could push it up. That there was some amount of energy difference between those levels. Basically, I've got my nucleus down here, all my plus charges. The closer you can get to the nucleus, the lower in energy you are. The closer opposite charges have gotten to each other. And so our electrons normally want to be as low down as possible, but you can lift something up. You can push an electron higher. but there's a set energy to do so. Only a photon of the correct energy can cause that interaction. As soon as it does, well, that electron doesn't like hanging out on high, and in fractions of seconds it will fall back down, and when it falls back down, it has to give off a photon. Now, when you crank a massive current through it to get it heated up and make your light bulb emit, say for sodium or hydrogen lamps, well, you can kind of cheat. You can throw electrons in and knock other electrons around, but they'll still relax eventually. And so you don't have to put light in to raise them. You can also put energy from an electrical current in to raise the electrons. When they relax, when they fall back down, though, they will give off light. And this is the light your fluorescent lamp or your sodium lamp or your argon and neon lamp or anything else are giving off. Well, that light has to have a specific energy. It has to have this energy, whatever the change in the orbitals, whatever the change in levels energy was. This means you can only give off certain wavelengths. Now, you can transition between various spots, and so I could have a bigger wavelength here, or I could fall all the way down, say from 3 to 1, and have a much more energetic photon. But there's only so many possible changes. Which brings us back to the line spectra. The higher energy would be the bigger changes. The lower energy would be the smaller changes. So as you have your orbitals, going from the very top to the bottom would be your biggest change. Going from a little down to the bottom would be a slightly less energetic change. Going from a little more down to the bottom would be slightly less. And then going from near the bottom to the bottom would be even less energy. What the Rydberg equation helped us see was that these lines were representing changes in energy of the electron around the nucleus. Now, unfortunately, Rydberg's equation only worked for hydrogen. We were never able to adapt it to work for any other element. And if we think about why for a minute, there's just one electron on hydrogen. And so that electron never has to worry about any other electron getting in its way. Other elements that have more electrons, well, which one's being excited? Where can it go? It's being repelled by other things, but as those electrons kind of move around their orbitals, that'll change how easy it is for things to move again. This becomes too complex. The moment there's more than one electron, we can't use a simple equation to solve it. So Rydberg's equation is phenomenal for hydrogen, but it isn't adaptable to any of the others. Luckily, it let us understand hydrogen well enough to then understand why it didn't work for the rest. Those extra electrons add too much complexity. But the idea was set. Where were these line spectra coming from? They were coming from the difference in energy between the orbitals. This also helped us start to see the photoelectric effect. If I want to knock an electron off, I need to take it from whatever orbital it's in, and I need to push it completely off. Oops. Well, if I want to take it from whatever the outer orbital it was originally in to free, there's a certain amount of energy to do that. Any light that had less energy than that only brought you, say, this far, well, you wouldn't have knocked the electron free, so no current flows. A red light, even less energy. It might absorb it, but it's not going to knock the electron free. The electron will just fall back down. The only light capable of causing the photoelectric effect was the light that had sufficient energy to push the electron all the way off. So it did not matter how many red photons you had, they could never reach all the way to knocking it off. You had to have the higher energy photon to succeed at pushing the electron completely off of the atom. And so this theory of electrons being at different energy levels around the nucleus. This is the core of photoelectric chemistry. This concept is what lets us understand bonding between molecules, covalent bonding, why certain molecules are stronger than other molecules, what holds them together. This all came about from Rydberg's equation and the line spectra.